sorry to those of you at home, I forgot to hit the record button. So we're looking at the amount of insulin here, and we're using this equation. The first question asks us what the 10 stands for. That would be our initial amount of insulin, which is 10 units. And then for the second part, it asks us what the number 0.95 tells us. 0.95 is the amount of insulin that remains, which means that if 95% remains, that 5% has been used up. So it tells us that the amount of insulin decreases by 5% every minute. Okay, so something really important in medicine and science, and you're just going to see this a lot, is this term right here, half-life. Has anybody ever heard that before? Okay, half-life is really important. Like I said, medicine and science are two places that it really shows up. So the half-life of a substance is the amount of time that it takes for a substance to be reduced to half its original amount. So how long it takes for there to only be half left. So remind me again here, Julian, how much insulin did we start with in this particular situation? 10, yes. All right, so if we're looking for the half-life, we want to know how much is left. 5, right? Half of 10 would be 5. So 5 is right here on our graph. If you go over here, right about here, it looks like we hit 5 units, right? If I go down here, what time did that happen? 15. So 15 minutes would be our best guess from this particular graph that we're given. Now, example 4 says use the equation to get a more accurate estimate. Okay? So this was just a guess looking at the graph. Maybe it's 15.03 and we just can't tell, right? I'm going to pull up Desmos. You guys don't have to get out your computer just for this right here. This is a when problem, right? When is there only half left? That's what you're asking when you're looking for the half-life. So I'm going to type in the equation, y equals 10 times 0.95, 0.95 to the x power. So we got this graph right here. And then we want to know how much is left? 5. So we're just going to put y equals 5 right here. And we're going to go over here and click 13.513. So 13.513. I feel like that graph's not really all that good that they gave us there. So the equation itself would give us a little bit more accurate estimate there. Okay, now let's talk about number 5. Theoretically, will the amount of insulin in the bloodstream ever be reduced to 0? No. There should always be a little teeny tiny bit left, right? Always. Now, in practice, if it's been 3 days since you took any insulin, whatever tiny trace amount that is left is not doing anything, right? You are going to be in bad shape if you haven't done that. It's not really doing anything. But theoretically, no, it would never go to 0. Because if I take half, it takes 13 and a half minutes for only 5 to remain. So take another 13 and a half for only 2 and a half. And then it'd be cut in half again, and cut in half again, and cut in half again, and cut in half again. And so you get like these teeny tiny decimals. Now in practice, it really doesn't matter. This is why, if you were to ingest an illegal substance that you were not supposed to have, and then they called your name out of the jackpot for drug testing, and you went up there to the office and they drug tested you, it would be able to tell that you had ingested that particular substance, even if it was 3 weeks ago. Right? Because hopefully, I haven't seen this in a while, usually we do not have students show up to school high. I mean, maybe it happens some, but most of the time, not high. Most students are not high at school. That does not mean they have not been high for the past 3 or 4 weeks, right? But drug tests can detect that teeny tiny bit that's left in your system, because as what your kidneys do is they filter out the toxins in your body, and your kidneys are going to produce the urine that you're going to give for that drug test. And so there's just this teeny tiny amount that's still showing up. I think mostly for the drug test that we use, they say up to a month. After, typically, if you have to, like, court says you have to be drug tested, it's going to be once a month, because it will still catch anything you've done more or less within that last month there. So that little bit. Now, after more than a month away, so if you did something you weren't supposed to do 2 years ago, it's not, I mean, theoretically, maybe it should still be there, but it's not going to show up on the drug test if you do that. So, so that applies in this particular situation. But you guys aren't going to have to worry about it, because you are not going to do anything that you should not do, or be ingesting any substances that they will be checking for anyway, right? Please tell me yes. Thank you. Okay, let's talk about this. This is an interesting application here. So, in 1989, the oil tanker Exxon Valdez ran aground in waters near the Kenai Peninsula of Alaska. Over 10 million gallons of oil spread on the waters and shoreline of the area, endangering wildlife. That oil was eventually cleaned up. Some of the oil evaporated, some was picked up by specially equipped boats, some sank to the ocean floor as sludge. But the experience had lasting impact on thinking about environmental protection. For scientists planning environmental cleanups, it is important to be able to predict the pattern of dispersion in such contaminating spills. Suppose that an accident drops some pollutant into a large aquarium. It's not practical to remove all water from the aquarium at once, so the cleanup has to take place in smaller steps. A batch of polluted water is removed and replaced by clean water, then the process is repeated. All right? So if you think about what is happening, and I'm going to relate this to what we did with our M&Ms on Thursday. Okay? Imagine that your M&Ms there is all your water, right? So whenever you have your M&Ms, the ones with the M's up, that was your oil that had been spilled, right? The rest of the M&Ms were your clean water. So whenever you took it out each time, you only took out the ones that were, you only picked out the ones that were up, but then whenever you went again, it was, there was more M&Ms that still showed up, right? So you're taking out a percentage each time. So like if you get, I always think that I need to like actually bring the bucket of oil and water so we can actually do this, but I never do. I always forget. And I've not actually tested that out at home to see how it would work, but because certainly a bucket might not mirror a whole ocean very well without waves and all of those things. I'm sort of mixing it up. But if you are taking water out of the ocean and running it probably like through a filter or a pump, right, to clean the water, you're taking out all the water. Some of it is oil, some of it is water. You run it through a filter. Do filters catch 100% of pollutants? Not usually, right? Especially if you want it to work quickly. If you want to filter it really well, you could probably get more of the pollutant out, but then it's going to take a long time for the water to go through, which is not good because all that oil is just spreading out in the ocean and making things worse. So you would pump the water through the filter. It might take out, let's say, 40% of the pollutants. You're pumping it back in. Then you're pulling more water out. And so you're reducing it a percentage, right? So the oil is never like 100% gone, right? But you can get it down back to acceptable levels where it's not affecting the environment through the cleanup. So let's look at this particular situation. The cleanup of oil in one location can be modeled by the equation 56,000 times 0.8, where Y is the number of liters of oil remaining in the environment and X is days. Okay? So what does the 56,000 tell us about the situation? That is our liters of oil. So it's 56,000 liters of oil spilt. Okay, so what percentage of the oil is removed from the water each day? No. 80 is the amount that remains. 80% remains. So that tells us 20% is removed each day. So you got to remember, whatever number you see there, that's the percent that's still there. So you got to do 100 minus that percent to get the part that's being removed. So the question says how much oil remains after 4 days. So for this, we just got to plug 4 into our equation. So if we type in 56,000 times 0.8 to the 4th, we got 22,937.6. That's not gallons, it's liters. Yes. Correct. So what we're going to see with decay, and we'll look at this here in a second, is if we put a 1 right there, I would have 587,863 liters of oil. That's more than I started with, all right? Because I only had 56,000 to begin with. So if we're looking at a situation where we want this to decay, we need to have a number right there for our B value that's less than 1, somewhere between 0 and 1. So on these decay problems, we're going to see this number right here should be a number that's between 0 and 1. If it ends up being more than 1, it's actually going to be growth. So it would be growing in that case. So that's a good question. We do not put the 1 in front for these. All right, so if a spill is considered cleaned up after 90% of the oil has been removed, how long does it take to clean up the spill? So, like we said, you're never going to get it all gone. So, let's say that the researchers that, now I made up this problem completely. I don't know what the actual amount is because I'm not an environmental researcher. But let's say that we've deemed 90% of it is good enough and the rest of it will sort of disperse and not affect the environment. So, how much oil is going to be left if 90 is cleaned up? 10. So if I want 10% of my original amount, that'd be 56,000 times 0.1, right? 0.1 would be 10%, which is going to give us 5,600 there. Basically just like 5 by 10. So if I can get the amount of oil down to 5,600, it would be considered cleaned up for this particular spill. So, again, this is a when problem. How long does it take? We can't solve that by hand, right? We have to use Desmos for that. So we would go type in our equation. Let me just do this here. Y equals, and I'm going to change that 4 right there to our X. I can't see it, so why can't I see it? Too zoomed in. Let's go over here. Let's change this to 56,000. We don't change the equation. So we leave the equation like it is. We are just, the 0.1 we're just going to use to find 10% of the 56,000. So we want to know when Y would equal 5,600. That puts this line right here for us. and we can see it would take 10.319 days. Now, I just made all of that up. It probably takes longer. Probably 56,000 liters is probably not actually enough oil to worry about if it's the ocean. Even though it sounds like a lot. So, all right, questions? All right. Okay. So let's just review something for exponential equations. We're going to add one thing in here. So we kind of already done this because Jada asked me that good question ahead of time. Y equals a times b to the x. A is our initial value, our starting value. Julian, what does our b stand for? What do we find for our b? Okay, who can help them out? What do we usually have for our b? It's almost our rate of change, right? It's our factor that goes with our rate of change, right? Our rate of change would be like we are decreasing by 5%. Our growth or decay factor is what we're going to call this here. And so, like, if we had a population increasing by 7%, our B would be 1.07. So it uses our rate of change, but it's not actually our rate of change itself. Now, so far, everything we had done was growth, so I'd only called that a growth factor, but it can be a decay factor as well. X is always some sort of time. And so we just talked about this. If B is greater than 1, bigger than 1, right here, the equation is an exponential growth equation. But if B is between 0 and 1, the equation is exponential decay. So, whenever we have growth for that B, we are going to do 1 plus the rate as a decimal. Right? If we have 7% growth, we do 1 plus 0.07 because that is 7% as a decimal. Right? If we have decay, what do you think we're going to do for our B? What? Say that again. We don't just leave it unless it's 50%, in which case it will work, but that's the only time. So, like, if we look at what we had back here, we had 0.8, but it ended up being 20%. We take it away from our 1. So we're going to do 1 minus our rate as a decimal. So it makes sense, right? If you're growing, you would add. If you're decaying, you would subtract from your percent. Okay, questions? All right, so let's look at some for these problems. We're going to do a couple things here. I'm going to do the first few together, and I want you guys to do the next ones. So some of this we should already know. We should be able to find initial value really well by now. We should be able to find our growth rate pretty well because we've already done that. Decay is going to be a little bit trickier. All right, so our first equation, we got y equals 5,000 times 1.07 to the x. Hank, is that going to be growth or decay? It is growth, right? So what is our initial amount? And what would be our growth rate? That is where we will find our growth rate, but it is not our growth rate. So our growth rate would be like the percent that we're increasing by. So we want to take away the 1 and then move your decimal so you just get 7%. So what I did there, each time, to find your rate, you take whatever number you have, whatever that B is, you subtract 1, and then change to percent. Here's the cool thing, it works even if it's the K. So if we look at the next one here, we've got 30 times 0.8 to the x power. 0.8 is less than 1, right? It's between 1 and 0. So we're going to have the K right here. Easton, what's our initial value? All right, and we said we're looking at decay rate. And so for our decay rate, we can do the exact same thing that we did before. We're going to have 0.8. We're going to subtract 1. When you subtract 1, it gives you negative 0.2. Move your decimal 2 places to the right, you get 20%. Now, is it negative? Don't say negative there. Saying that it's decay covers the fact that it's negative. If you say something like the amount of oil is decaying at a rate of negative 20, decay and negative would actually like be double negative and make it positive, right? All right, for 12, Vince, what's our initial value there? It's missing, isn't it? What number is it going to be when it's missing? 1. Okay, so if you don't have an initial value, it would be 1. Let's see. Wade, is this going to be growth or decay? Decay. All right, so you can do the same thing that we've been doing. We're going to do 1/3 minus 1. What is 1/3 minus 1? If you have a whole, you take away 1/3. It'll be 2/3. It's going to be negative since this is sort of in the backwards order, right? So negative 2/3. Now, if I want to make this a percent, I really just need that to be a decimal. So if I do 2/3, you got 0.6 repeating, which hopefully you already knew. And you will move your decimal 2 places to the right. So you'll get 66.6 repeating percent. All right. Let's see. Caroline, for example 13, what is our initial value? Very good. Not writing. And are we going to have growth or decay for this one, Caroline? Nope. It's growth because 2 is bigger than 1, right? So it's going to be growth. So it's the same process every time. Take that 2, subtract the 1. 2 minus 1 gives you 1. Change it to a percent by moving it 2 places. You get 100%. Okay? Try the next 4 on your own. Julian, get your head up. multiply these 4. Case 20, decay rate is 88%. For 15, initial value is 3,500. Growth rate is 4%. 16, initial value is 2. Decay rate is 60%. Example 17, initial value is 600. Decay rate is 0.7%. Okay. Any questions on how to do that? Alright, we got a couple more things to do. Alright. Quick warning, quick word of warning. When you buy a car, it is going to depreciate. It is not a good investment. Investments are things you put your money in to gain money. It is a necessity that you have to get around. Okay. So, unless you buy a car that is like a classic car that you're going to sit in a garage somewhere and rub on, if you actually drive the car, it's going to decrease in value. Except for, as I was telling you guys a little while back, car prices are crazy right now, and it may not actually apply for this particular moment in time because there's a shortage of cars. But eventually, unless the world falls apart, eventually we should get back to the typical where when you buy a car, it starts to depreciate, right? So you need to be careful with this, because if it's depreciating really quickly, it is going to lose value quicker than you can pay it off if you're making payments on it. So you might have a car that you still owe $60,000 on, but it might only be worth $50,000. So that means you've got to pay the bank back $60,000, but if you sell it right now, you would only get $50,000. Meaning you have to pay the bank $10,000 if you sold that car. Plus, well, you get the $50,000 from selling it. And then you have to pay an extra $10,000. So normally you should just keep paying on it and get it paid off. Or if you wreck it, so if you have a vehicle that you owe the bank $60,000, you total it, it's worth $50,000. How much money is insurance going to give you for that car? Huh? No insurance pays attention to how much you owe on the car. Ever. Unless you have special insurance. Unless you have more. When you bought the car, if you buy gap insurance on it, which is what we're talking about, that gap, that money, it's only worth $50, but you owe $60. So when you buy the car, if you buy gap insurance, it will cover this. But that's not your motorist insurance. Like, that's not your car insurance, right? So car insurance, if you don't have gap insurance, car insurance is only giving you $50,000 for that car. But you owe the bank $60,000 for that car. So you're going to take that $50,000 that the insurance gave you, and you're going to pay off what you can, but you're still going to owe the bank $10,000 that you got to pay for for a car that you don't even have anymore. So that's why they try to get you, if you're going to have a gap, they'll try to get you to buy gap insurance. Gap insurance is expensive and costs you a lot of money. Your best bet is to have a down payment on your car so you never get the gap in the first place. So don't just go and say, I have $0. What can you get me payments for? Go and say, I've got $10,000 already. Or ideally, you just save up the money first and go buy the car, if that's possible for your particular situation. That's ideal, but if you're not in a situation where you can do that, then you would need to have, if you have a down payment, then you already paid $10,000 on this car, so it might be worth $50,000, but you only owe $40,000 on it, so it's unlikely that you'll get in that gap situation if you have a down payment first. So if you're going to buy a car that you're going to make payments on, save up some money first, all right? Because it is going to depreciate, it is going to lose value, right? So Harley buys a new car for $20,000. The value of the car depreciates at a rate of 12% per year. So we need to write an equation for this. So we're going to have y equals initial amount is $20,000. And so if it is depreciating at a rate of 12% per year, that means you're losing 12% of the value each year. How much are you keeping? 88. So you'll have 0.88 to the x power. That's our equation. All right, so if we want to know how much money the car will be worth after 5 years, we're just going to plug in 5, right? 20 times 0.88 to the 5th. And, then 20,000. So we get $10,554.63. So the car is worth a little more than half of what you paid for it after 5 years. This is very realistic. That would actually be a car that's retaining its value fairly well. Especially, and it, of course, condition and how much you've driven it play big factors here. So those would be things you'd have to consider, but that would make our equation too complicated for us to deal with at this point. When will the car be worth less than $20,000? All right, so this is a when problem. When problems are not ones where we just plug the number in. We're going to go over here to Desmos. We're going to change this to where it's an equation by putting that as x. And then in the second line, we're going to type in y equals 2,000. And we got 18.012 years. So you're still losing money at the same percent. It's just not as much money, right? So if you think about what's happening here, let me actually. So like it took about 5 years for the car to be worth half. If we did 5,000, at 5,000, it takes 10.84 years, so almost 11 years. So it took 6 years for it to cut in half again. If you did, instead of doing 2,000, if I did 2,500. 100. We got 16.267, so it's like 6.5 years to cut in half again. So if you buy a cheaper car to begin with, it's still losing at the same rate, but it's gonna, not be as drastic as far as the amount of money goes. All right, we're gonna do this real quick. All right. A town has a population of 13,000 people that is decreasing at a rate of 1.3% per year. What will the population be in 12 years? So our equation is going to be 13,000. What are we going to use as our rate? What? It's not 87 because of that decimal point right there. If it was 13, you would be correct. Let's grab our calculators. We got 100 minus 1.3 is going to give us 98.7. So we would use 9.987. Right. And in this case, it's 12 years, so we type in 12. So we have 1,300 times 0.987 to the 12th power. We've got 11,110. We'll go 111. Oh, look at that. Round to the nearest person. And then if we want to know when the population will be less than, get rid of this stuff. Change this to an X. Less than 10,000, we would just type in Y equals 10,000 here. And we could see 20.05 years. For that. Okay. Questions?